Welcome, 8th graders, to the Explainer. Today, we're diving straight into the physics of motion. We'll be using some super cool concepts from the NGSS and visualizing things just like you'd see in those awesome PhET interactive simulations. Think about being at a massive skate park, right? You're flying over ramps, weaving through obstacles. Well, how do we actually scientifically measure all that epic motion? That is exactly what we're going to figure out today. Let's get moving. Here are our 3 learning targets for today's Explainer. First, we'll distinguish speed from velocity. Second, we'll read time and position, or time and velocity data. And third, we'll use slope or rate of change as evidence. All right, first up, speed. In physics, speed is strictly defined as magnitude. Now, what does that actually mean? It just represents how fast an object is moving, completely ignoring its path. So, when you see a cheetah sprinting on a nature show or a race car just blurring past the finish line, you are witnessing speed. It really doesn't matter if they're running in a giant circle, zigzagging all over the place, or going in a perfectly straight line. It's all about that raw magnitude. Think of a car's speedometer. It just tells you the magnitude, like the raw number of meters per second. It literally doesn't care where you're going, just how fast you're getting there. Next, we have direction. You can think of direction as the compass for our motion. It gives us the necessary orientation or the specific path of that movement in our physical space. I mean, think about it. If you're giving a friend directions to your house, telling them to go 3 miles is kinda useless unless you tell them to go 3 miles north, right? Direction anchors our movement to the real world, whether that's north, south, left, right, up, or down. And that brings us to our next core concept, which is velocity. Velocity is defined as magnitude plus direction. Adding that directional component completely changes how we measure the motion. You aren't just moving fast anymore. You're moving fast toward a specific destination. Velocity is absolutely crucial in the real world. Like a meteorologist tracking a hurricane, they don't just care that it's spinning at 100 meters per second. They need its velocity to know exactly which city it's heading toward. Air traffic controllers rely on velocity too, not just speed, so airplanes stay safely on their specific routes and, don't crash into each other. So comparing these two side by side makes it super clear. Speed is magnitude only, like meters per second. But velocity, that's magnitude plus direction, like meters per second north. Velocity must always include that directional unit. If you leave out the direction, well, you're just talking about speed again. It's a tiny addition in words, but a massive leap in how much information you're communicating about an object's journey. Let's cement this with a quick worked example. Imagine you're in a car cruising down the highway, and your speedometer reads exactly 50 meters per second. We know exactly how fast it's going, so that is our speed. But watch what happens the moment you grab your compass and note your heading. By declaring you are driving exactly 50 meters per second east, you've officially upgraded that standard speed into a precise velocity. Just adding that one word, east, gives us the whole physical picture. Okay, now we need to know how to actually map this motion out, which brings us to graphing. Our first graphing term is time. Time is our independent variable that constantly moves forward. We almost always plot time on the horizontal x-axis because it just marches on steadily no matter what the object is actually doing. Whether you're sprinting, standing perfectly still, or flying to the moon, time is always ticking away at the exact same rate. Our next term is position. Position is the specific location of an object relative to a starting point at any given moment in time. Think of it like this. If you walk out your front door to head to school, your front door is the starting line. Your position is the exact number of meters away you are from that door at a specific second. If you stop to tie your shoe, your position stays the same while time keeps ticking. It's your exact coordinate in the world right at that moment. So if we track a moving object over time, a really clear pattern emerges. Looking at our data here, at 0 seconds, the position is 0 meters. At 1 second, it's 2 meters. At 2 seconds, it's 4 meters. And at 3 seconds, the position is 6 meters. Do you notice how the position predictably increases by the exact same amount, 2 meters, every single second? This tells us our object is moving at a perfectly steady, constant pace away from its starting point. Now, in math class, you've probably heard of slope. It's the steepness of a line on a graph. Mathematically, it's calculated as the rise over the run. Basically, it tells us how much the line goes up vertically divided by how much it goes across horizontally. A really steep slope means a rapid climb, while a jump-in slope means a slow, gradual increase. We're going to take that pure math concept and bring it straight into the science lab. Here is where math actually meets physical science. Let's talk about rate of change. In kinematics, that mathematical slope on a position time graph translates to the real-world rate at which position changes over time. And that rate of change? Well, that's our velocity. The steeper the slope on your graph, the faster your object is moving in the real world. It's kind of the ultimate aha moment where the numbers on a page perfectly describe the physical motion of a skater, a car, or even a rocket. Let's actually calculate this together using the points 0, 0, and 2, 4. To find the slope, we take our rise over our run. So we take our final position of 4 meters minus our initial position of 0 meters and divide that by our final time of 2 seconds minus our initial time of 0 seconds. That gives us a rise of 4 meters over a run of 2 seconds, which simplifies perfectly to 2 meters per second. Boom! You just used mathematical slope to prove velocity. By simply tracking how the position changed over time, you calculated exactly how fast that object was traveling. Now, before we test your skills, we need to tackle a massive misconception that trips up a lot of students. Constant motion does not always mean constant velocity. Changing direction means changing velocity. Picture this. If you're strapped into a roller coaster moving at a constant speed of 10 meters per second in a massive perfect loop, your velocity is actually constantly changing. Wait, why? Because your direction is shifting at every single degree of that loop. Even though the speedometer on the coaster would be frozen at 10 meters per second, your physical heading is shifting from up to upside down to down, changing your velocity the entire ride. All right, it's time for our first check for understanding. Listen carefully. If a train moves at 80 kilometers per hour west, then turns north at 80 kilometers per hour, did its speed change? Did its velocity change? I want you to pause the explainer right now. Really think about the train's motion and choose your answer. Welcome back. Okay, here is the correct answer. The speed stayed the exact same at 80 kilometers per hour. But the velocity absolutely changed because the train went from traveling west to traveling north. The magnitude stayed constant, sure, but that new direction means a brand new velocity. If you got that right, you are officially mastering the difference between these two tricky concepts. Let's try check number 2. Think back to our position time graphs. What does a completely flat horizontal line indicate about an object's rate of change? Go ahead and pause the explainer again, look at your notes if you need to, and choose what a completely flat line means for an object's physical motion. And we're back. The answer is a flat line means a slope of 0, so the object is perfectly at rest. The rate of change is literally 0 meters per second. Because the rise is 0 over whatever the run is, the position isn't changing at all. Time is passing, but the object hasn't moved a single millimeter from its spot. Let's lock this in with a quick recap. Speed is magnitude only, while velocity is magnitude plus direction. Constant speed can still mean changing velocity if the direction shifts. And finally, on a position time graph, the slope equals the rate of change, or the velocity. We've covered a ton of ground today, so here's your final transfer question to truly test your mastery. If you run 5 meters forward and 5 meters back in 10 seconds, what is your final velocity based on total position change? Think critically about your starting and ending position here. Grab your notebook, write your short answer down right now, and share your reasoning with your class. And before I let you go, think about this. Right now, as you sit perfectly still in your chair, the Earth is hurtling through space at over 67,000 miles per hour. Are you ever truly at zero velocity? Keep wondering, keep calculating, and I'll see you next time on The Explainer.